Okay, so MMI711 sequence models in multimedia, and this week we are going to talk about embeddings. What is an embedding? Because embedding is an important concept for many sequence models. And while we are doing this introduction, we are going to delve into some introductory level natural language processing. And if we have time this week, I've got slides for it. I'm going to introduce attention, but we are going to cover attention actually next week because there are many things to cover regarding attention. We'll see. If we have time, I'm going to talk about it today, or maybe I'm going to leave it till next week. Okay, so this week, before we delve into attention, we are going to talk about some introductory level natural language processing, although it is not within the scope of this course. I mean, this is not an NLP course, but since we are dealing with sequence models, they are closely related to the concepts of deep NLP. And we are going to discuss word-to-vec because word-to-vec is a type of embedding. And there's this thing called embedding. We are going to be discussing this embedding a lot, and we are going to do a simple live code on which I introduce PyTorch's embedding layer, which is just another neural network layer, guys. And after we do this, the encoder decoder models, sequence models that belongs to the field of NLP will make more sense to us. And just we make a better sense of the sequence-to-sequence models of NLP, we will delve into the subject of attention. Attention is quite a new subject. I mean, it was first introduced by Bahdanao, a guy. This is the first author of the paper, Bahdanao et al. And the others, I should have said, in 2014, officially published in 2015. This, if just like I said, if we have time this week, I'm going to start with that attention, but attention is, you're going to see this next week, it's a broad concept which has different techniques. I mean, there is attention, Bahdanao attention, or recurrent model of attention, there is self-attention, context-based attention, etc. We are going to make a clear introduction to them, and we are going to cover them next week. Okay, so NLP. I mean, just like I said, this is not the course for NLP, and there's a course for NLP, Tuğba Hoca's course, which is text analytics. And in that course, most of the subject is entirely covered, but without touching into what deep NLP is and where it stands in sequence models, it is difficult to get the entire picture, because what I'm trying to give you is, in a course like this in sequence models, to give you the entire picture. And actually, we are going to cover this introductory level NLP concepts, and covering those introductory concepts will help us model some sort of sequence models which do not fall into the field of NLP. I mean, NLP is, language modeling, natural language processing. However, in sequence modeling, there are some sorts of signals which are like categorical, but do not fall directly into the field of NLP. For example, one of your friends taking this course, and my master's student, he's doing anomaly detection on bank transactions. Well, it doesn't look like NLP. However, you need to make, the data is categorical, and you need to make a proper embedding for the model to work as a sequence model. So what we're going to do is we're going to cover the concept of NLP that relates it with the sequence models, and starting with embeddings. The embedding part will be important for us because it's this fundamental title. Understanding embeddings in NLP will help us understand why transformers are very powerful in the following weeks. Okay, let me get back to the slides. So NLP is natural language processing. It's a subfield of linguistics, computer science, and artificial intelligence. So it's concerned with interactions with computers and human language, basically human language, because we've got different sorts of languages, So in particular, the aim is to understand or program computers to process or analyze large amount of natural language data. So the goal is we speak and the computer understands. So, so if the aim is to make a computer that understands the contents of documents or the language, it is not an easy task because there are contextual nuances, very little tiny details that makes the language so sophisticated. We just with a little word or a little letter, maybe sometimes we change the meaning a lot. So how to do this? How to do it? That's the problem with the definition of NLP. So I'll get back to NLP. So NLP is an interdisciplinary field. I mean, cognitive scientists or psychologists are interested in the field, and artificial intelligence guys are also interested. And recently, there has been an interest on deep NLP. Deep learning is also interested because of these sequence-to-sequence models. We'll get there. So, as you can see, this is fundamental. This figure shows the fundamental relation between different fields of NLP. Okay. So, most of the scientists, when trying to understand NLP, they categorize NLP into three main eras. The first years, it was when NLP emerged, actually, was the 50s, when the first computer scientists tried to model languages as a sort of automata. Automata is these finite state machines, regular expressions, the computational definition of mathematical language. If you have taken a course on switching or automata or computational theory, you know what I'm talking about. If you haven't, well, there's a way to represent algorithms just like a language. And it was the first approach. So up to 90s, scientists mostly have been working on modeling the language symbolically. And this symbolic representation, because of the methods, are deterministic. This is very important, guys. Most of the automata, finite state automata, is deterministic. I mean, there are fuzzy logic and that stuff as well. But when we talk about the title of regular expressions and automata, it's deterministic. So the idea was to teach the machine how to understand languages in the same way we humans have learned how to read and write. Because the way we read and write, I mean, we are very complex beings. I'm not talking about the neural connections we do, but the methodology that we use to read and write is quite deterministic. We can put up the rules. Actually, by using those rules, my elder daughter, who is in first class of primary school, is learning how to read and write. There are rules, there are certain rules. And if you can model that rules, you can learn the language. That was symbolic. So this was quite similar to what computational linguists do, because they use rules, lexicons, and semantics to teach the machine how to understand the language. The approach was limited, guys, because the exceptions of a language are quite extensive. And whatever you do, it is quite difficult to handcraft a deterministic rule-based model of a language. People have done this, people have used this, but it was not working correctly. I mean, we didn't have a proper machine translation engine with this method. By the way, symbolic methods in not only in NLP, in the entire artificial intelligence field is growing has been growing for the last 2 years. So symbolic AI will strike again, in my opinion. We'll combine with deep learning methods, and it will strike again because it has some advantages, this symbolic AI. But in today's NLP, it's not practically used. So the second approach was statistical NLP. Actually, if you're my age, like if you're like something 40 years old, the people who worked on NLP, I mean, my friends, my colleagues, when in their PhD, did work on that stuff. It was mathematically modeling language using some non-deterministic methods, stochastical methods, or statistical methods. And the famous one is hidden Markov models, actually. Hidden Markov models have been widely used. So it is like you have data and you are trying to find out a method to model that language, which is not entirely transparent, unlike the symbolic NLP. Okay. And today's subject is neural NLP. So before we get that, if you're interested, I provided some sources about symbolic NLP and statistical NLP, some survey papers. And today, starting with the last decade, just like AlexNet, people start to work on techniques which are based on deep learning for NLPs. And actually, recently, there has been some breakthroughs. For example, Transformers 2017, like it's less than 4 years now, is one of the breakthroughs. But before that, the efforts, started around the beginning of 2010. So the idea is using deep learning network style machine learning methods in natural language processing. So what are we going to learn from it? Let's see. What is it that is very important for us? I strongly recommend Tubajo's course, and I strongly recommend this online course as well. Just like Stanford has this CS 231 for computer vision and convolutional networks, they've got this CS 224 for natural language processing by Christopher Manning. He's a very famous guy, and I strongly recommend you watch it. I've taken some of their slides in my slides as well. If you're into NLP, I definitely recommend this course. So what is neural NLP? It is that's not our job, but I'm going to just start with the main intersection point of neural NLP and our problem, which is they are sequence-to-sequence models. So you provide a sequence and you get a sequence. However, unlike the multimedia sequences, the sequences are tokens of language, and tokens of language are usually modeled as words. Because if you want to tokenize a language, well, it's already tokenized by words, because we don't sync to each other. We don't create melodies to each other when we sync. We just create discrete tokens and we transfer them. So that's why neural NLP is a sequence-to-sequence model in which you exchange tokens. Good. How to model these tokens then? Is it as simple? That's the question. The idea is about the tokens, guys, because that's the main difference. Because if it was, I don't know, the frames would have been themselves, we would feed them to a convolutional network, then an RNN, which is just the CRNN, as you just have been using in your midterms or your projects, or you've learned in V5, whatever. That was the main problem of NLP, guys, especially deep NLP, because when you're dealing with a neural network, if you want to feed an information to a neural network, you have to somehow transform the token into a form which can be directly fed to the network. Okay, so that's why computational linguists, before deep learning as well, they tried to study this meaning over words. What is the meaning over word? Because we are tokenizing the language with words. So what those individual tokens represent was the most common linguistic way of thinking for meaning. Okay, token, meaning. Because that meaning is important for us, because we are going to bring that meaning of meaning into a definition of similarity between the tokens, right? Okay, so previously, the common solution was to make a large corpus of the language where we classify, categorize the meanings, and the shared effort was the WordNet. It's a website. In WordNet, we have the meanings of all words, those tokens of the language, and the synonyms as well. This is very important, because when you create a large corpus of synonyms in a language, synonym means the words that have the same meaning, you are relating some of the words to each other. So you're creating a definition, a similarity, a representational, something representative between the tokens, right? This is important because if some of the tokens are similar to each other, maybe there's a mathematical way of representing it. And that was, the first effort was the synonyms defined in WordNet. But we still didn't know how to, I mean, the field didn't know how to feed that similarity to a neural network. That's where we get Embeddings. This is WordNet, I mean, this is a website. It's run by Princeton. It still exists. I mean, if you need a proper corpus of language, you can go on that there. However, the thing is, when we are defining synonyms, we don't define a proper way of similarity. I mean, in Manning, in that course, Manning provides in just lectures in Stanford's video slides. There's a good example about proficient and good, because in WordNet, proficient and good are kind of synonyms. But you can say to a person, you're a good person, and what you mean is totally different than you're a proficient person. So having the idea of a synonym is not totally enough. And if you just delve into that synonym stuff, for example, wicked, badass, nifty, wizard, they all have different meanings in different contexts. So that is the language, that is what the language is all about. We need the way to model the relation between the tokens properly so that when we feed it to a neural network, it would make sense for us. And actually, this is not the only problem for NLP. If you're dealing with any categorical knowledge, you need to do this. Because that's how we do it. We humans, I mean, my kids do it that way. When they understand a certain meaning of a word, a new meaning of a word, they are very surprised. They add it to the dictionary. And when they add it to the dictionary, those kids try to update all the relation of that token with the other tokens so that they can make new words and they speak funny and make jokes about it. That's what the language is. So what was the previous approach we had? I mean, you remember what we've done previously in our live codes was when we want to tokenize words, we created a data structure in PyTorch, which was called vocab. I mean, short for vocabulary, but the structure was vocab, remember? And in vocab, we represented each word with a one-hot representation, in which you've got some number of zeros where there's only a single one value. So it is like in your dictionary, in your vocabulary, you have n words. In that case, your one-hot representation is n by 1 or 1 by n. And here it's 1 by n, doesn't matter. So for each word, there is a single position one. So this makes the one-hot representation. That was what we've done. The problem with, for example, if you have number of words in vocabulary like 500,000, we will have 500,000 long vector, which is not nice. I mean, you wouldn't want to process 500,000 word vectors when you're doing NLP. That wouldn't be computationally efficient. Is there another way? Yes, there is another way. So the problem with this representation is it doesn't have the notion of similarity. Just like we said, there is this synonyms, right? For example, in Stanford slides, it is motile versus hotil. They're totally the same. However, the orthogonal distance, I mean, the Euclidean distance between them, yeah, it could be anything else, any type of distance, is the same to another word as well, because another word would have been something equals 0, 0, 0, 1 is somewhere else. And the distance between them is, I mean, everybody's distance is equal to everybody. So there's no natural notion of similarity in one-hot vectors. However, in language, there is. There's a complex relation between tokens. That's what that's what the language is all about, just like we said. So what we've done previously in our codes, remember, what we've done was we didn't care. We just fed it to an LSTM. And we wanted the LSTM to learn that similarity. And in those cases, what LSTM did was it learned the relations, I mean, the similarities between the words, plus it learned what the sequence problem was as it learned the sequence problem additionally. So it was like we are pushing the LSTM to model the sequence and to learn the similarities between the tokens at the same time. So it was like we were pushing the LSTM, the recurrent model, too much. However, if there was a way to encode the similarity of the tokens and feed it to the LSTM, we would have made the world easier for the LSTM, right? And it would, in my opinion, be similar to extracting some high-level features from the data and feed it to the RNN, just like a CNN RNN model. Because in CNN RNN, we don't feed the pixels directly to the RNN because it's very difficult to model the pixels for the RNN, whether it's LSTM. LSTM cannot understand the pixels. Let's use a CNN to encode them to some high-level representation, then feed it to LSTM. Well, that's a kind of a similar approach. If we could encode the representation first, then feed it to an RNN, maybe the model will work better. Actually, that feature extraction step in NLP or in any categorical data is called an embedding. So when we're feeding the source language input, instead of feeding one-hot vectors, maybe we could convert it to another mathematical representation where the similarities will matter. And that's called an embedding. Okay, so for example, I'm not telling you how I did it. I'm going to talk about it. A word will not be represented using only a bunch of zeros and a single one. It will be represented by a number of real values in a and by one vector, and not necessarily being the size of the vocabulary this time, because you can create different values. So these are called word embeddings, because it is an embedding. We are mapping the index of a token in a vocabulary to a vector. That's what embedding is. Okay, just if you didn't know it already, most of you already know this, but this is what embedding is, guys. This is good because if you can do it, you can create the similarity of words in a representation like this properly, so that it represents the real relation of that words in the language, right? So this is a very nice figure I've taken from Stanford slides. What they did was an embedding is created for English language and n-dimensional. For example, this is 1, 2, 3, 4, 5, 6, 7, 8. It's a 9-dimensional representation. So you have 9-dimensional vectors for each token word. Okay, so you can calculate the Euclidean distance between them. Imagine for these words, for all of the English words, I have these representations. Okay, I calculate the Euclidean distance between all of them. They are 9-dimensional, right? So they are flying in a 9-dimensional space, and they've got distances. Well, it is not possible to visualize 9-dimensional spaces for human beings, guys. I mean, if you're not Protos, it's difficult for you. What people do in those cases is they make a list of those mutual distances between words, and they project those distances to a 2-dimensional space so that it represents the distance measure intuitively. Okay, so this is a projection representing that similarity between those words. What does this mean is, for example, in a proper representation of the English language, I'm not telling you how this was done. We are going to get there in a 2D projection of it. That when that word vector is projected to a similarity space of 2 dimensions, for example, come and go become very close to each other. For example, need and help are close to each other. Say and think are close to each other. Being, been, had, his, have, all these words of the English grammar are close to each other. So it makes sense, because when we understand the language, that's what we do. Because imagine I'm speaking English and my English not perfect. You don't have to imagine it. My English is already not perfect. I make a grammatical mistake. I say, instead of saying I was there, I say I were there. You still understand, because was and were are very close to each other in that space of your representation. That's pretty much simply what word embedding means for NLP. And people have theoretically thought that this would make the job of an NLP, deep NLP model easier when we feed those features to that sequence-to-sequence model. And that was correct, by the way. Okay, but how to obtain this? I mean, we understand what embedding is, what is it for, what is the intuition, how to obtain this. The algorithm to obtain it is called word-to-wake. It is a fairly new algorithm, less than 10 years. It's a framework for learning word vectors of a language. The idea is, that's the resolution that we're going to cover this. We have a large body of text. Every word in a fixed vocabulary is represented by a vector, just like that vector. And we do algorithmic stuff to designate the places of those vectors, which I'm, with caution, trying to stay away from, because this is not the scope of this course. So they go through each position of text in all the sentences of the corpus, and they calculate some things, and they create a vector space where the similarity of the words are properly represented. That's what word-to-vec algorithm is. So in the end, if you're interested, I provided a blog. That's where I first read it from. So it's a combination of models used to represent distributed representation of words in a corpus, say C, set of tokens C. So what you have is, in the corpus, you have sentences, because word-to-vec uses the sentences, the position of the words in the sentences. And it provides these vectors, guys, nothing else. Actually, in general, this is called an embedding, because this is not the only way to do it. And there are different ways to implement word-to-vec. There are different word-to-vec algorithms. For example, these are the most famous two ones, the skip-gram and continuous spec of words, which are beyond the scope of this course. What they do is they provide a vector representation for a given set of sentences, which we usually call corpus in NLP literature. Okay? So, just like I told you, I'm not going to get into the details of it. However, as people who will be modeling sequences, most of the sequences you model will not be signal data. So they will be categorical. You will need tokens. You will need a sort of algorithm to embed it. That's why we are going to talk about embeddings today. So that's how we keep out of the NLP stuff, but still learn ways so that we can operationalize categorical sequences for our models. So we're going to talk about embeddings. So before we do that, let's discuss what this word-to-vec is good, and we're going to get to embeddings later. So the output of the word-to-vec is the vectors we use for the tokens. The representation is quite peculiar in the sense that it creates a similarity space between the words, which makes sense for that language, and that's the beauty of the corpus. So it vectorizes words. So it makes the input to the deep model a vector space of tokens where the similarity information is already learned. The example I've given, the analogy I made was the CNNs creating the high-level features from pixels for the LSTM to process. It is exactly the same. So word-to-vec can be thought of a feature extraction step for a NLP system. I mean, it wouldn't be entirely true to say that, but I don't think that it is not wrong as well. I mean, we can safely say that. So a neural word embedding word-to-vec is a neural word embedding. Represent a word with numbers. So word-to-vec is similar to encoder in the sense that it encodes words. It's like a feature extractor. I mean, you can make many analogies. I don't want to make many analogies because it will confuse you, but it is best that you understand the idea of word-to-vec. The word-to-vec is feature extraction step for a language. Okay, well, we need that as well. I'm not dealing with natural language, but I will be dealing with bank transfer packets which have some fields. Actually, most of the fields are categorical and they are tokens to me. I will need to do that as well. One thing could have been one-hot vectors. Yes, you can always try one-hot vectors, pushing the LSTM to do its job. But maybe finding an embedding will make the LSTM perform better because it's a feature extraction state. Actually, before I finish my stuff with NLP, the NLP was not only about languages, the spoken languages. NLP people are working on codes as well, modeling codes. So, and in Python, there are very nice implementations of word-to-vec for different corpuses. Because, for example, in C, in computer languages, we don't have sentences, but we have expressions. And expressions are written line by line. And people have implemented word-to-vec vectors using skipgram model for C language. And when you're trying to model codes, or there are different studies for code-based NLP, they try to find malicious code and they do find viruses, etc. That's how they do it. So, why this is important for us? And let's get to where NLP intersects with us. NLP is a part of deep learning and sequence modeling because of the sequence-to-sequence models. And actually, one of the early studies of sequence-to-sequence models that used encoders and decoders was the study by Cho et al., which was a language translation model. It's a statistical machine translation. It was a learning phrase representation for RNN encoder decoder for statistical machine translation. It was an RNN encoder decoder. And it was revolutionary in many senses because it was one of the earliest papers of entirely pure deep NLP. And it was one of the early models of encoder decoders for all sequence modeling, not only NLP. So this paper stands at a very important intersection point for both NLP and for both sequence modeling. And as sequence modelers, even if it is not a language problem, we use encoder decoders for modeling different stuff. You know that. And for NLP guys, it was the first encoder decoder approach such that today, any sequence-to-sequence model that deals with language is an encoder-decoder model, including the transformer. They are all encoder-decoder models. There's not an encoder-decoder model in deep NLP. There are different architectures, but in the end, they are encoder-decoder models. So this is an important paper because they proposed the very first RNN encoder-decoder that consists of two recurrent networks for modeling the language. Good. And after that, this idea was quickly applied to different, instead of RNNs, these Sutzker and Vinyals, they used LSTMs to make it work better. And this was one of the earliest papers because this is the paper of Google's in 2014. And maybe you'll remember that in 2014, Google Translate started to work perfectly in one day. Not perfectly, it is working much better today with transformers, but in 2014, people start discussing, well, those translation guys, they're going to be jobless kind of thing. That was the paper. These guys from Google, they applied that encoder-decoder idea to this LSTMs. And when they were applying it, they used this embedding idea as well. So embedding, the word-to-vec embedding, found in 2013, and this sequence-to-sequence models using the LSTMs in 2014 combined, they created that breakthrough of machine translation, one of the important breakthroughs of NLP and sequence modeling as well. I don't have to tell you the architecture. It's quite simple. It's an LSTM encoder, decoder, nothing else. I mean, it's sometimes, even today, it is surprising to me because the idea is quite simple. I mean, you find an embedding obtained from the words about, I mean, depending on their frequency in sentences and their relations with their neighbor tokens words. You feed it to an LSTM, to another LSTM, then it translates perfectly. I mean, it doesn't look like a very complicated idea, but it is. I mean, it just, the field, the literature arrived there step by step. Good. So this is how the great journey of neural NLP started with EVs. Okay. So, before I finish everything with NLP, I'm going to talk about the loss functions of NLP as well, because that's something is important as well. So imagine I'm training this. While I'm training this, I'll need to do it in a supervised manner because I've got a large corpus of already translated text. I mean, there are many books, thousands of books, which already have been translated from Italian to English. I can use that corpus, right? Okay, but when I'm doing this supervised learning stuff, how am I going to evaluate the loss at the end of this network? How am I going to penalty it? It's because it's not just vectors, values. And in the last 10 years, people have come up with very, not last 10 years, last 20 years actually, NLP. It started with statistical NLP. They have come with some accepted measures of evaluation matrix, two of which are the bleu and rouge, which are blue and red in French language. They're simply a measure of precision or recall in the language. We are not getting into the details of it as well. But however, whenever you have a token sequence like a language, you get back to these measures to use them, to evaluate them. In language, they are being widely used. So if you're into NLP, if you take Tubaja's course, you'll definitely learn them. But if you have to immediately learn these evaluation matrix and word-to-vec algorithm, I strongly recommend you study this idea of n-grams, skip-grams, and continuous back words. Those three, I want to say algorithms, ideas, approaches actually dominate the evaluation metric and the encoding as well. Good. Okay. So the loss is calculated somehow, we don't care. When we get deeper into the architecture, what we see is we have the language, we have the latent representation, the meaning here, and we've got each word as an output until we have the end of sentence. There's a question. No, there's no question. There's a problem with the mic, I guess. Okay, so the idea was these encoders in machine translation was the flexibility in length. This encoder-decoder approach compared to the previous approaches of machine translation, single LSTMs or the statistical methods, they provided a means for longer dependencies. So longer dependency means being able to handle longer sequences, which means in practice for machine translation, longer sentences were being translated better with these models. Okay, so however, the evolution of the literature has shown us that even this approach needed some improvements, and actually, which was the attention. So this Sutskever's paper was succeeded by this famous Badanaus papers guy. This one, sorry, where is it? This was Badanaus paper, which for the first time introduced the idea of attention. At this point, I'm going to press stop because at this point we know what encoder-decoder models are, recurrent encoder-decoder models. We know how sequence-to-sequence models work. We today learned how deep NLP emerged from encoder-decoder models, and that's why we are also interested in them in this course, because sequence models are actually basically recurrent encoder-decoder models mostly, and they're non-recurrent encoders as well, just like transformers we are going to learn. But for other sequence models, we've come to that place as well. Well, at that place, there was another breakthrough, which was the attention. Attention I'm going to talk about if I've got time today, or starting with next week, we're going to cover the entire idea of attention. But before that, I think the only thing we haven't talked about is this idea of embeddings. Okay, for machine translation, it is word to vec, and we don't care because it's the scope of the text analytics stuff. But as a person who's going to do a sequence model on a categorical data, how am I going to do the embedding? What is an embedding? There's a so-called embedding layer. What is that? Actually, embedding layer is, it's not here. Embedding layer is actually an object in Torch, which means it's a type of a layer, like a linear layer, like a ReLU layer. So what is it? I'm going to talk about this. And you are going to learn the very definition of the embedding and the embedding layer, which is just a linear representation layer, actually, using live code. So I think I'm going to stop here. If you have not any questions, then in the next video I'm going to start the live code session. Any questions?